So today we are talking about linear functions, slope, and applications. Here's your list of objectives for today and what we're going to cover. We're going to dive right in. So something is considered a linear function if it can be written as y equals mx plus b, where m and b are constants. And notice that x here does not have any exponents on it. So that's one of the most helpful things to think about, okay? Now, what happens when there's no exponent on the x is when we look at our xy tables, the change in y is the same every time. Notice in this example, it's 50 all the way down. And it leads us to have a perfectly straight line on the graph. Whereas when you have a nonlinear function, then the change between y, the difference between the two rows, goes up or down each time it changes. It's not the same. That is when we start to see a curve in the line like we have here that curves upwards. And so that we call nonlinear. So if you need to check if something's a linear function and you're given a table of values, check that your x's are changing the same and your y's are changing the same. And if your x's are changing the same but the y's are not the same, that means it's nonlinear. Okay. So when we look at graphs of lines, y equals mx plus b, this is called slope-intercept form, mostly because there's a slope and a y-intercept. And so when your function is f of x equals mx plus b, or y equals mx plus b, same thing, your b value comes from where it intersects the y-axis, our y-intercept. And notice y-intercepts are points, right? 0, comma b. So it's the y value of your y-intercept. So where on the y-axis does it cross that line? And if there's no y-intercept, it's f of x equals m times x. It goes right through the origin. Hasn't moved up or down at all. Now, m is the slope. The slope of a line is the steepness. We'll get into a few more details of that in the next slide. But m gives us how much we're vertically pointing upwards or downwards in the steepness of our line. So, slope specifically is our rise over run. So if you have a point x1, y1 and a point x2, y2, then your slope is the change in y over the change in x. So essentially it's this formula right here, y2 minus y1 over x2 minus x1. That is one you should memorize so that you know the difference. And that is exactly how much we go up and then over whenever we're thinking about the slope of a line. It's change in y over change in x. So find the slope of the line that passes through the points 0, 2, and 1, 5. And this is our first example. So we know our slope formula, m equals y2 minus y1 over x2 minus x1. And so we're going to label our points x1, y1, x2, y2. So then we have 5 minus 2 over 1 minus 0, which is 3 over 1, which is 3. So our slope m is 3. M equals 3. Now I just want to point out that points 0, 2, and 1, 5 can be written in this format, and you'll see that on your homework, where it's the same thing. Our input is x, which is 0, output is 2, or input is 1, output is 5. Those correspond to points as well. So feel free to always just write them down as points like this. Okay, moving on. Now, find the slope and y-intercept of the line with this equation. And remember before, we have y equals mx plus b, right? And so we're actually just going to compare this to the formula and pull out, well, what is the role of my m and what is the role of my b? Okay, well, 2 is in front of the x in the same way that the m is in front of the x. So we can immediately write down the m, my slope, is 2. Now my b, I have a plus b, and I'm doing a plus -1 here. So my y-intercept is not -1. My b equals -1. My y y-intercept is the point 0, comma, -1, right? Y-intercepts are points, so 0, comma, -1. And that's it. You're going to have a few of these on the homework. We're going to do another example now. So again, we write down y equals mx plus b for visual reference. And we know that this is in the place of our m, and right here is our b. It's negative again. And so we have our m, which is our slope, is negative 3.8. Notice I don't include the x, right? M is sitting in front of the x, so I grab the thing in front of the x. Okay, and then my b value is negative 0.25. So my y-intercept is 0, comma, negative 0.25. Now, the other way you might see these is written like this, where it's not perfectly y equals mx plus b. We have to do some manipulation to it to make it look like that. So essentially, we want to get y alone when this happens. Okay. So when I see this, I'm going to add the 7 to both sides. And we get 3x minus 6y equals 7. Now I'm going to subtract 3x from both sides. And I have negative 6y equals negative 3x plus 7. Okay, and then last step, divide by negative 6. And I get y equals negative 3 over negative 6x minus 7 over 6. So the negative, this minus 6, since I'm dividing the whole thing by it, I distribute it to both items, okay? So negative 3x divided by negative 6, and the plus 7 divided by negative 6, which gives us the negative 7 over 6. And we'll take this one step further because negative 3 over negative 6 can be reduced to 1/2 x minus 7 over 6. Okay, well, that is a formula we can work with. Okay, so if I bring that back up here, I have y equals 1/2 x minus 7 over 6. So my m is 1/2, and my b is negative 7 over 6. So my y-intercept is 0, comma, negative 7 over 6. Done. So again, it just became about, okay, we need to rearrange the terms to get to the y equals mx plus b that we recognize, and then we can pick up our m and our b and answer the question. So when you have a positive slope, it's going to slant to the right. You're going to read it from left to right. You're going to notice that as I go from left to right, it slants forward, essentially. It falls forward almost, and it raises up. Whereas when I have a negative slope, it's going to go, and when I read left to right, it's going to go in the downwards direction. Okay, this is supposed to be a horizontal. I'm reading horizontally left to right, and my slopes all go in the downwards direction when I leave left to right. So that's just the difference. A positive slope slopes upward, a negative slope slopes downward. So that's something you should be able to recognize when looking at these. Now, whenever we graph a function, you want to find the y-intercept and the slope first. Then we can actually graph it. So here I read off that my slope is 1 over 5 and my y-intercept is 0, comma 2. So I'm going to start by plotting the point 0, comma 2 right here. And then I'm going to use the slope 1 over 5 and know that that means rise over run. Okay, so rise means I need to go up 1 and then I go over by 5. Okay, so I went up 1. I'm going to use a different color here. I go up 1 and I go over 5, and there's my second point. So there was my first point, here's my second point, happens to be 5, comma 3, and I draw my line between the two. And that's all we need. If I had a ruler, I could extend it as far as I wanted and keep going. But essentially, you plot your y-intercept, and then you use the rise over run to know you rise 1 and run 5. Now we have a particular kind of function that's called the identity function. That's where my y value always equals my x value. And it always looks just like this function here. But we need to think about, well, what is my m and my b? Well, would you agree that this is actually 1 times x plus 0? That means that my slope m is 1, and my y-intercept is 0, 0. Okay, so I plot it at the origin, and then I need to go up 1 and over 1, and I plot the next point. And that's how I get my line for the identity function, y equals x. I just have my 2 points, I draw the line between them, and I have it. But sometimes you need to uncover your m and your b, notice, right? We had to put in that m is 1 and b is 0. Without changing the value of the function, we can at least identify those items then. So let's do this next one. Graph y equals negative 2 over 3x plus 4. Well, that means that my slope m is negative 2 over 3, and my y-intercept is 0, 4 from the plus 4. So let's start by graphing 0, 4, which is right there. And then remember, this is rise over run. So that's a rise of negative 2, which means I go down by 2 to here, and a run of 3 over 1, 2, 3 right here. And so now I have my second point. I can draw the line between the two. Could I have kept going? Sure, I could start here and I could go down another 2 and over another 3, down 1, 2, over 1, 2, 3. And if this was a perfect line, maybe I could redraw it for you. It would hit right through that point as well. So sorry I can't draw a perfectly straight line. You only need 2 points, but you could keep going. Go down 2, another 3, down 2, another 3, and you can draw out as many points as you want. You only need 2 in order to actually graph a line. So we start with the y-intercept, and we go down 2 over 3 once, and we have our second point. Now we're going to talk about some more horizontal and some more particular lines, namely horizontal and vertical lines. So any horizontal lines, remember horizontal means a line going this way, vertical means a line going this way. Okay. When we have horizontal lines, it's always of the form y equals a number b. When we have vertical lines, it's always equations of the form x equals a number a. Okay. Those are always going to be true, and you're going to see some examples moving forward. So if a line is a horizontal line, then the change in y for any 2 points is going to always be 0. If it's horizontal, that means they have the same y value. So it's x1, y1, and then x2, and my y2 is just y1 again. So as soon as I put that into my slope formula right here, I end up with a 0 on top and a 0 over all. So my slope is 0. So my lines always look like y equals 0x plus b, which is why the 0 falls away. We get y equals b. Naturally, b is our y-intercept value, right? And so it's always just going to be a constant. Y equals a constant. That's why it's called a constant function. Now with vertical lines, it's not my y's that are the same, it's my x's. So I have something like x1, y1, and then x2 is just x1 again. So I have x1, y2. So when I do that, I get this as my slope function, but that gives me something that is undefined, which means my slope, we say, is undefined for vertical lines. Notice this is also not a function, right? Because it doesn't pass my vertical line test. So we won't ever ask you about y-intercepts of vertical lines. You can just say they don't exist as well, and that the slope does not exist here because it's completely vertical. So looking side by side at these, when we have a horizontal line y equals b like this one, our slope is always 0, and our y-intercept is always 0, b. And for a vertical line, x equals a, which is not a function, notice, the slope does not exist, or sometimes we say undefined. Okay, so here's a perfect example. Y equals -2. My slope is 0, and it's just a horizontal line at -2. Notice all my y values are the same at -2. Whereas on the right-hand side, I have x equals 4. I have a vertical line at x equals 4, and they all have the same x value. So when you're given a table then of values, you can tell when you have x equals -2, that means my x value is always -2, and y can be anything because x is always -2. That's the only necessary component of this equation we're looking at. Y can be anything. Okay, so then that means that everything is filled in at x equals -2, which gives us this vertical line. And just remember, not a function, and my slope is not defined. But here's what the table would actually look like. Alternatively, when I look at y equals 5/2, that means my y values are all the same, and my x values can be anything. And it's going to be a horizontal line like we have here. Notice our slope is always 0, and this is considered a constant function. Now, why do we use slope? Well, we use slope for a few different applications. And this first one I'll tell you about is to figure out the grade of something. So the grade of a road is the number expressed as a percent. It tells us how steep a road is on a hill or a mountain. A 4% grade means it rises or falls 4 feet for every 100 feet that you go forwards. So, and here's a really good graphic of that. It actually, quite interestingly, federal law states that every vertical rise of 1 foot requires a horizontal run of 12 feet. So that is the maximum grade that you could get in any kind of incline. And if you wanted to find the grade of something, well, you would think, okay, a rise of 1 foot. Find the grade. I guess they're giving us 3 inches for some reason. I'm not exactly sure why. But if you're given 3 inches of rise and 42 inches of run, we can reduce that fraction and get 7.1%. Okay, so essentially our slope, as we know, or this grade, is always rise over run, 3 over 42. You put that in a calculator, and that's what we get as our percentage. Next application of slope is to consider it as an average rate of change. So the average rate of change between any two data points in a graph is given by exactly the slope. And sometimes we abbreviate it AROC. That's what you'll see from me. But it's just change in y minus change over change in x. So that's y2 minus y1 over x2 minus x1, like we've been doing. Okay. But we now have to think about it in terms of a word problem. So in this example, let's think about it for a second. The number of people participating in a federal supplemental nutrition assistance program has increased from 7.2 million in 2000 to 47.6 million in 2013. And the graph on the following slide illustrates this upward trend. Find the average rate of change in the number of people using food stamps from 2000 to 2013. So let's look at that graph for a second. Notice which one's on my x, which one's on my y. So my x are the years, and the y is the number of participants. And this graph isn't exactly straight, but the average rate of change will tell us, well, if I had drawn a straight line between these two, what would the slope of that line be on average? So let's do that. The 2 points that we want to grab are 2000, 17.2. That was given in the problem. And 2013, 47.6. So if we do our change in y, we get 47.6 minus 17.2. Change in y over change in x is 2013 minus 2000. Now that is going to be 30.4. I'm getting out my calculator. Sorry, everybody. Here we go. 47.6 minus 17.2 is 30.4, like I thought. Just want to double check my work, over 13. And when we reduce this, 30.4 divided by 13, we get 2.3. 2.34. Okay, as a decimal. So 2.34, that means this sentence at the bottom here. The average rate of change over a 13-year period had an increase of 2.3 million participants per year. So every year, the number of participants went up by 2.3 million on average. That is what we have just answered. So now we move on to this next example, again, an application of a function. So there is no proven way to predict a child's adult height, but a linear function could be used to estimate it, given the sum of the heights of the child's parents. The adult height m in inches of a male child whose parents' combined height is x in inches can be estimated with this function, and it's given there in m. An adult height f in inches of a female child whose parents' combined height is x. The inches can be estimated with this function. Okay, that's a lot of information there. You even heard me stumbling over my words. The point is, the combined height makes up x, and the output, m, is in inches the height of the child. Similarly here, combined height is x, and the output is the height f in inches of the female child. So if we wanted to estimate the height of a female child whose parents are the combined height of 135 inches, well, it asks for the female child. Okay, so we need that f function. And we're going to plug in 135. And one moment, please. All right, I just had to go back to grab what the actual function was. 0.5 x minus 2.5. Okay, so if I plug in 135, I get 0.5 times 135 minus 2.5, which gives us, let's get the handy dandy calculator out, 0.5 times 135 minus 2.5. That gives us exactly 65 inches. So the idea here, the point we're getting at, is that we can use linear equations to actually give us approximations. So we can actually start to relate how different people have related to their parents and combined height, and actually figure out an approximation of what a female child might have for her height. Now for our last example here. Here we actually need to come up with the linear equation. So let's read through it and then we'll work through it together. Here we have Richard is considering relocating to an assisted living facility. He learns that there is an initial community fee of $2,250 and a monthly charge of $3,380 for level 1 care. Write an equation that can be used to determine the total cost C of T for T months of level 1 care. Then find the total cost for 20 months. Okay, so the two important numbers we're given here is that there's an initial fee of $2,250, and then every month after that, he gets a charge of $3,380. So if I'm thinking about C of T, let me make that look like a C. C of T equals, well, I have a one-time charge of $2,250. Anytime you have a fixed cost like that, that is what is going to not have a variable next to it. That is a one-time fee. It does not happen every month. It just happens at the beginning, so that's our initial charge. Every time beyond that, we get charged $3,380 for every month following. That means that's the one that has the T next to it. And so this is what we get for our equation. 2,250, again, for that initial cost, plus 3,380 times T for every month after that. So if I want to think about, well, what is C of 20 then? I get 2,250 plus 3,380 times 20, which gives me, let's see, 2250 plus 3380 times 20. Ooh, $69,850. That's pretty expensive assisted living, but seems expensive. I don't know what it really goes for. But that is how we write down its equation and how we evaluate the total cost for 20 months. Let me know if you guys have any questions. I'm always available by email.